Welcome everyone, and thanks for attending the MRL webinar series from the Materials Research Laboratory at the University of Illinois, Urbana-Champaign. We're glad to have you here from various parts of campus, US, and the world. My name is Rick Hosch, Senior Research Scientist at the Central Research Facilities at the MRL, and I'll be your host for today. Our facilities are currently open to researchers, and we are in the process of training new users. We are fully complying with CDC, State of Illinois, campus, and MRL safety guidelines for social distancing and use of proper PPE equipment. If you're not currently a user of our facilities, you can become one by submitting an online research proposal through our website, mrl.illinois.edu, and select Become a User from the main menu. Feel free to contact us if you need any help. Today we'll have a webinar on X-ray analysis entitled Top 10 Mistakes in X-ray Analysis and How to Avoid Them, given by Dr. Mauro Sardela, Director of Central Research Facilities at the MRL. This will be the last presentation for the time being of this webinar series. The series has been running every week since April 2nd. We have had a total of 19 presentations from 17 presenters with a combined worldwide attendance close to 2,000. We thank you for attending this event, and we thank all the presenters. Also, thanks to Julie Tenhave for the event organization, and also Steph Adams for the communication outreach support. The webinar series will return sometime in the near future, covering various topics of materials fabrication and characterization. If you have any suggestions for topics that you might like to hear, feel free to contact one of the staff. Video recording from each of the webinars are being posted in our YouTube channel. When in YouTube, just search for MRL Facilities where you can find the presentations. In addition to other training material for various techniques such as nanomechanics, AFM, XRF, SEM, etc. You can find videos at our webinar website, go.illinois.edu/MRWebinars. In the Zoom software interface, please enter your questions in the chat box, which is typically located at the bottom of your screen. We will address all the questions at the end of the presentation. So today I'd like to introduce Dr. Mauro Sardela. He received his BS degree in physics from the University of Brasilia and his Master's of Science degree and Master's of Science degree in physics from University of Sao Paulo, Brazil. In 1995, he received his PhD degree in materials science from Linköping University in Sweden, working on thin film growth, X-ray scattering, and device fabrication. Mauro was also principal analyst at Evans Analytical Laboratories in California from 1996 to 1998, working with the surface analytical techniques. In 1998, Mauro joined the MRL as a research scientist and later senior research scientist in the X-ray analysis core. He became the director of central facilities at the MRL in 2015. Mauro has been involved in research on semiconductor thin film materials, X-ray scattering, wood degradation process, in addition to radiation safety studies for the National Academy of Science and the US government. So with that, I'd like everybody to welcome Mauro, and let's get started.
Thanks, everyone. Okay, over the past maybe 2 or 3 decades, training users or researchers in the field of X-ray analysis, doing research in that area, we have identified, some common mistakes or problems that people run into when they do the work, the analysis using this technique. So I put together a top 10 list of those. This webinar is going to be a little bit different orientation, direction that you see. We're going to do the whole thing upside down or backwards, because we'll start with that data that has problem. Then we kind of we'll bring the theory or the basic concepts of how to understand that. And then we'll show you actually how to provide the correction for what was the problem originally. We'll follow a sequence of complexity. The first one is absolutely silly. It's very common. People come to us and say, oh, look, I was doing the same material, doing the same process than someone else in the literature, but my data looks really, really different. For example, like this case here. So how can it be? Look at I have some difference in peaks, but basically look at the peaks are totally in different location here. How can you explain that? I mean, the reason is very simple. To understand that, we need 2 concepts. The first one is the concept of reciprocal space. And the need for that is because basically what you see coming out from the XRD data, like in this plot here, you have like, you know, a diffraction angle, the detector position versus the intensity that's collected. Basically what the XRD system shows you is not a direct representation of your crystal, of your material, but nevertheless, it's actually what it sees in a space that is like called reciprocal space, and the correlation between the two spaces is done basically through a Fourier transformation. If you have a material where you have some periodicity here, which is the atoms are arranged in a periodic fashion, so it's common to describe that periodicity by using imaginary lattice plans in this case here. So what this will correspond in the reciprocal space will give a certain spot in reciprocal space. If you actually use a different set of plans, and of course, you'll get like a different spot in the reciprocal space. As you see here, that as you start actually looking at information in different plans for the atoms in the crystal, basically you start tracking different getting different spots in the space. If you use, for example, plans that in different orientation, you get a reciprocal space spot there. Those little dots that are marked here is actually what you measure when you do a data collection in your X-ray diffractometer. We go more in detail of that, but the basics for quantification is Bragg's law, which basically here you have on the left, you have the crystal or the partial part that's ordering the material. Here you have the reciprocal space representation of that crystal. And then basically if you start with an X-ray beam impinging on the crystal, it's equivalent in the reciprocal space to an incident wave vector. And then if you get a diffracted out, which is collected by the detector through an angle here, you have like a scatter wave vector. And basically the diffraction process is described by the difference between these two wave vectors, which is called a scattering vector. And if you assume like in diffraction that you have a energy conservation process, the absolute values of these two wave vectors are the same. And then with the angular notation that you have here, you come back down to this relationship that was due to both father and son, Bragg, famous Bragg's law. The power of this technique actually is invaluable because basically, if you know the wavelength of the radiation that you are using for your measurement, and then if you can actually measure the angular position of the detector that's collecting signal. So and if you measure intensity there, you can actually go back through this equation and calculate something that's at microscopic level, which is the separation between the atoms here, the atomic planes. This de-spacing, what we call, is extremely powerful because that's a signature of the material and allow us to actually retrieve lots of different properties of the material. So it's very common, we're gonna hear about that, something called a Ewald sphere. So you represent this scattering process when you are actually like dreaming and navigating inside this reciprocal space. You can actually draw a Ewald sphere, a sphere that has the radius equal to that scattering vector. And then basically the process of scattering is that actually as the sphere moves across that space, every time that it touches one of these points, you get an intensity. So remember the concept of Bragg's law is very important because what we're going to use next is to look at the data. So then when we talk to the researchers, say, well, let us see what exactly were the conditions, the measurement in the literature was done and compared to what? To your, most likely the people in the literature will have like sometimes a different wavelength, a different type of radiation than the one that the researcher is doing. So of course, they will show up at different locations. You can see here from Bragg's law, you can understand that a different wavelength will actually give you a peak at a different location for the same D material property. So then basically you start to understand the problem, and then you can pick up the data from the literature, you can use this conversion, and then when you convert that data to your data, you see there is a perfect matching here in terms of the peak position. Of course, there are actually differences in terms of the relative intensity and so on, but now in the end of the day, everybody is happy because that data that looks so different in the literature, actually it's just a question of different radiation. One final example here from the Percharski and Zavali book. You can see the same data acquired with moly radiation and copper radiation, the same sample. You can see here that the data acquired in moly, it actually it uses a much more tight, narrow range in the angular range here for the detector rather than that. So watch out for that. It's a silly case, very easy to actually resolve, but we see that enough to qualify and to be in our gallery of the top 10 here. And the message that you should take home is that before you compare your data to whatever is in the literature or a collaborator has done, ask exactly how the measurement was done. What is the supporting material in the paper, and so on. Verify the radiational wavelength. That's important in the data involved. This is particularly important if you are comparing data acquired in a lab source versus a synchrotron radiation. It's also always a good measure also to convert that data to units of Q, which then you don't need to worry about the wavelengths. It's very important if you are actually dealing with iron materials. Typically, iron can be measured like using cobalt radiation to prevent fluorescence. Also, if you are looking at data that was acquired using temperature chambers or pressure chambers, many times they actually need to use a radiation that's much more penetrating. So moly will be a candidate. For pair distribution function data, you need to go to very high values of Q space. You need a silver radiation. But by far, the most common radiation in the literature is copper. So make sure that when you report your data, you do mention that, and that is pretty much exciting. Now, with that simple case out of the way, let's go to a little bit more subtle problem where people observe like peak shifts. So someone does a measurement in the data, and basically this is what he was expecting. The data of the material is here, and then he's typically comparing that with like a reference, which could be a reference from the ICDD, International Center of Diffraction Data database of pure reference materials. And then in some case, he expects his data to match the line from the reference, but sometimes what he or she sees is a shift on the data. And then he does not understand. It's very common. They'll come back to us in the lab and say, well, what is going on? Is it like a physical property? Because it could be that this shift on the peak position could be a real physical effect, but how can we actually separate that? To understand that problem, we need to go back to the concept of like a X-ray based instrument configuration. One configuration that's very commonly used is Bragg-Brentano focusing configuration. In that case, the X-ray beam actually, it's not drawn parallel. It's actually a beam that diverges, going the surface, and then basically it actually focuses back in the detector. So, and then you have this concept here, like this blue circle, which is the diffractometer circle, where actually the sample actually will stay here, and the detector is going to be moving. The tube will be moving around. So basically, that's a configuration that's extremely important, very common. It gives you very nice, well understood peak shapes, but also it has the problem of being very sensitive to a small error in the position of the peak. Okay, you see like a shift in your peaks. There could be many reasons in that configuration. The first one is that maybe the instrument you are using is misaligned. So maybe when they actually calibrated the instrument, the beam that should pass at the center of the instrument at 0 is actually shifted. But that will actually introduce a constant shift for all Bragg angles that you measure. Another problem is like the sample not being flat. So because of that configuration, it can be a problem. The vertical divergence of the beam, that means the beam is spread perpendicular to the diffraction plane, could be a problem as well. Or it could be very well that instead of putting the sample at the center of the instrument, you actually made a mistake and put it a bit higher or lower. There is an equation for that. Or there is a problem like your sample is too thick and it has like various absorption. You have to, versus the depth, which is another problem that you need to take into account. Most of the X-ray instruments that you come to use, you come to like a central lab or shared facilities, all these problems are taken care of, and most of the problem that you may have is you. the instrument operator, and it's very easy to create an error there. So what that can be done. So basically you have a calculation here where you have the X-ray beam, the diffracted beam. This is where it should be, the beam coming up in the detector if the sample was exactly at the center of rotation. But if you put the sample, in this case, higher or lower, you can see that the beam is going to be measured at different angle. And from the trigonometry here, you can see that that delta, that shift actually is proportional to the displacement S that you introduce. It's proportional to the angle that you are measuring, and it's proportional to the cosine, which makes the whole thing opposite. So basically, it's more sensitive to at low angles, and it's less sensitive at high angles. We'll show you that soon. And it's inversely proportional to the radius of the goniometer. So for example, if you start using instruments that are very small, like tabletop instruments, you may have a much more problem in your hand here. So how does this impact your data? But you tell like, well, I'm sure I put the sample, exactly the sample holder, at the center of the instrument. In many of these instruments, the position is pretty much locked. What did you do wrong? What did we do wrong? Sometimes as you put your powder, you have to make sure that the surface aligns exactly with the edge of the holder, because that's where the zero rotation of the beam, if you put too much or if you put too low, now you can see here that your sample is actually displaced. And then what you get there, these are like graphs showing the impact of that, as of the variation in the angle versus the misplacement that you did. It's actually a linear function, and versus the angle that you are measuring, it makes the whole thing much worse at low angle. If you are dealing with polymer materials, for example, soft materials at low angle, you might be in more trouble, because then you start talking like a 0.02 angle displacement, which goes actually clearly above of actually the accuracy of the instrument. So one question that is very common is how can you separate the two effects, like, misalignment of the instrument and sample displacement. Remember that the misalignment of the instrument, shown here in blue, is linear. It's the same across all the angles, where the displacement sample, the displacement is actually, it varies. So you have here at 28 degrees here, and if you go to higher angles, you can see here that the effect is smaller, but the shift because of misalignment of the goniometer is actually much, it's constant there. So there you go, that's like a trick you can use to analyze that. The parallel beam configuration, where instead of focusing beam is a parallel beam, it's very useful because it tends to minimize that. We also have like an aerial detector 2D configuration in our systems. For the parallel beam, just one example here, you see that in this case, the sample was initially at the right position, then was 1 millimeter higher, 1 millimeter lower. You can get a shift of 0.4 degrees at low angle, and as you go to higher angle, that is smaller, but it's still appreciable 0.18 degrees. And here is the plot that we have showing, like, for this instrument, for every single angular range, what that impact that you can cause on that. And of course, it's larger as I have higher displacement there. So in a nutshell, be very careful how you mount your sample, especially at low angles, and talk to the instrument manager if you see a problem on that. Number 3, okay, data collection settings. People complain, well, my data is very noisy. I collect data and I try to do quantification and nothing is coming up right. What is going on here? Now, you have to understand what is going on behind the data collection. So basically, you are counting photons, which is a statistical event. And if you do all the math here, it's governed by a Gaussian distribution of the number of photons that is actually counted here and distributed in this curve. You have the concept of standard deviation, but most important is the relative standard deviation. And you can see on this relationship here that is inversely proportional to the number of counts. So the more counts you have in that particular data point, the better your chances to get like a better accuracy, a lower standard deviation. And this is the graph of this curve here showing you, actually, I have some table here, that if you actually are dealing with a data that's just one count, your standard deviation is very poor. But if you start having data that lists like, 1,000 counts on that data point, basically we're talking about a 3%. Now the challenge is that it's not all the data that will give you all that information. Here is one example. 2 impacts we have. One is for the scanning speed. and the other for step size. The scanning speed is how fast you collect the data. Some people that are always in a hurry, they'll collect the data at very fast speed. In this case here, look at how the data is noisy. There are even some kind of noise in the data here that you don't know if this is peak or not. The accuracy on the peak shape is going to be poor, especially at the low intensity, and quantification is not going to come out any good. For like, a quick and dirty run where you want to find out where your peaks are, basically, or identify, it's pretty good, or like a preliminary scan. But if you want to do like a more refined, a cell refinement, a quantification analysis, you do need to acquire data longer. In this case here, look, there is almost like 100 times better, is lower data. The same thing with the step size in most of the instruments. You actually go to a smaller step size, the scan is going to be slower. You see on the top here, the guy has collected with 0.05, and in the lower one with 0.005, you see the data is much more well-defined. In this case here, the researcher will even miss these double peaks for two phases in the course data versus the other one. And of course, you can use this statistical analysis to estimate using like 2 sigma, what kind of accuracy you have. I mean, if you are going to do quantification, it's very important that you have as many counts as you can. But you may be having a problem, like some people try to say, okay, then I know, I understand now everything. The best solution is to use very small step size and go extremely slow. That is not always the answer. You're going to spend up like, end up spending like days or like a whole night or a weekend collecting data. You have to find the best compromise. If you have broad peaks, you probably are going to be able to use large step size, and because you don't have sharp peaks, but go slow so that you can enhance the signal above the background. If you're actually having sharp peaks, so maybe you can go with a fast scan because the sharp peaks tends to have high intensity and you are more interested in your step size. If you have a mixture of them, good luck, because then you have to find a compromise both of them. So the best way to set your scan is that look at the PDF database for your reference where your peaks should be. Watch out for possible overlaps of the peaks because then you have to have a small scan size, a small step size. Carry out a fast preliminary scan first to see how things are going, and then you do a more detailed scan. Now, it's very helpful that the modern instruments nowadays, they tend to be much faster for data collection. So we got the question about the actually Bragg's law, the instrument configuration, good manners, good practice for data collection. How about sample issues? What can actually be, what are you doing wrong? How your sample can be affecting the quality of the measurement in the way. So for this, it's very important to look at the basics of the diffraction process. I hope you guys can see a video where the angle of incidence omega is changing, the detector is changing. Dark here in the center is your powder sample. As you actually change those angles, you see that you are going to higher angles and peaks start showing up. Those peaks indicate that your material is crystalline. This is the important information for you. But please look on the right-hand side. This is important. Number one, as you actually change the angle of incidence and the angle of the detector, you are actually changing those angles of the wave vectors, which means that you are probing the scattering vector Q along a particular direction, which is always normal to the planes, and most of the time perpendicular to the surface. Well, in a nutshell, what you are doing, you are only probing the orientations that are parallel to the surface. You can see that here on this colorful diagram, where actually doing a measurement, you are just probing the grains or crystallites that actually have orientation parallel to the surface. And then you ask, well, how about the other one? I'm missing all of them? Yes, my friend, you are missing them, but that, if you have just a small amount of material, you are definitely missing them. Some of the peaks might not show up in your data, but if you prepare your powder well enough, small size, and then you make sure that this material is randomly distributed, this particular grain that you are missing here is going to show up down in the sample with the planes parallel. Another thing that you have to see here that's important, as the incident beam is increasing, notice that the footprint of the beam here, the area in the surface is going down it's actually becoming narrow, but you go deeper. So if you set up your instrument properly so that you have always sample inside the cavity of the detector, basically you're always collecting from the material. Keep this in mind for future reference, and we go from that. One parameter that is very important is a slit, an opening that we set here just as the beam gets out towards your sample. It's called divergence slit. The setting of this is very huge impact because that determines how long the beam shines in your sample at low angles. So this is something that you do need to talk about that with your X-ray lab manager, and basically make sure that you are actually covering the proper area in your sample. Why? Because the following, now one concept you have to remember here is if you actually are collecting data and the sample is totally randomized, like in this case here, you get full rings. But if you actually have just a few crystals, a few grains oriented, or like a single crystal, you may get spots in the diffraction ring, or you may actually get like, broken rings. That has an impact for us as you start doing scans, because in one case you can completely miss the information. In the other case, you actually can collect all the information. That has an impact on the number of particles in your powder. You see here that we have like, in case if you have a lot of particles here, all the orientations are random. So you get this ring here fully continuous. So it doesn't matter a lot if you scan, if when you do a scan, you cover this direction or the other direction. But if your number of particles is small, you end up having broken rings or spotty diffraction rings. Then you have a problem where you collect your data. Here is like a dimension, typical dimensions from a powder cavity that people use. And then you can see here that if you have large particles, this is the number of particles you can fit in that. So as you actually grind your sample to actually smaller size. And we always recommend you at least like, go down to 50, 30 microns, for example, see that you can start having much larger number of particles. So then it's much easier to interpret the data, you understand the data there. So that is very important. Three examples for you. One is this again from the excellent book by Pecharskis and Zavalli. In this case here, they collect the data using incorrect divergence slit. So basically, they have very little amount of sample. The X-ray beam was shining also on the sample holder. And also they put very coarse power, very large size. So look at here that the data, which is like the dots, are actually not matching the calculated pattern. And if you look at the difference here, there is like big spikes showing like a big difference. That's why sometimes you measure your data, say, well, the intensity looks different from what actually I had in the literature or the reference. Second case, they actually put more material. They could match that. You see that the peaks now start actually getting closer to the calculator, but they still have the problem of coarse powder. And they did not even do a sample spinning to average the grains that are being measured. So this is the final where they do the state-of-art sample preparation, 10 microns particle size, speed the sample using correct settings in the instrument. Look, outstanding matching between actually the expected data calculated and what they observe. So if you see differences like that, please talk to the instrument manager and be aware of this. It's very important that if you have small quantities of materials, many of the users do not have like a large amount of powders to use in the analysis. Make sure that you use the proper sample holder. There are sample holders that have low background. So basically there is no signal from the sample holder to interfere in the analysis. And if you can grind your sample to a smaller size, that will make a whole world of difference in data interpretation. So the other topic that we see, we talk about like the measurement conditions, about how to prepare your sample, but people still get confused about something called crystallite size or grain size. The common question is that, well, I did my measurement here in your lab, but my crystallite size are not the same as I see in the literature, or that my colleague has obtained like, 5 years ago when he was doing this project. Also, I did SCM on the same sample. And I mean, my grain size are different. What is than what I get in the X-ray? What is going on there? Well, this is a very common problem. There's confusion there. We get this question almost like on a weekly basis. First, you have to understand the concept of crystallite size. Basically, what you see here is that the inverse between real space and reciprocal space, where actually, if you have a material like a single crystal, where like the volume of the crystal that has a unique periodicity is very large, the Fourier transformation of that will give you just a small spot. When you do the measurement on that spot, you get a sharp peak. Now, if you do like with polycrystalline materials where the crystallites are small, so when you do that integration, you see like a large distribution, a large distorted peak, and that gives you, when you integrate this and collect like one-dimensional data, you get like a broad peak. I have the things cute there. Another one that you actually, a confusion that you have, okay, what are you actually measuring? Are you measuring crystallite size, grain size, particle size? What you're strictly measuring XRD is crystallite size. And basically, most of the time, it's equal to the grain size, but the grain size is not necessarily equal to the particle. You may have a particle with different grains and different orientations inside, the subgrains they call. So basically, if you use a technique like an SEM, a SAX, or a DLS measurement, you are actually measuring particle size, and your XRD or TM data uses actually your measured crystallite. There is also another thing that, well, is this, how come I'm getting different density or size? Well, you have to understand that XRD does a large average in your material, where some of these techniques are more local and they average in volume versus, or they average in number. So keep that in mind when you compare across techniques, across lab. We talk about crystallite sub. How is that measured? Well, it comes as a free bonus on your data when actually you collect the data to identify what you have in your material. The information is already there. All you need is the width of the peak, the position of the peak, and then you use this equation called shear equation. There is a constant here with shape factor close to 1, the wavelength of the diffractometer, which is a constant, the position of the peak, and the width of the peak in radians. So you can calculate that. Now, again, as in X-ray anywhere, things that seems too simple, they have gross approximations there. Number one, look at that. You are not accounting for other effects on this broadening, like the strain defects, dislocations that could play a role of that. It's a very simplistic approximation. Second, remember that when we measure those peaks, this is just in one direction, in the direction to the surface normal. You are measuring the grain size in only that direction. And if you have inhomogeneous distribution of size, you are not picking up that information. So when you compare your data, for example, with the TM, ask, for example, what direction they measure the grain size. And here again, you see a nanoparticle, very broad peak. The inverse relation means very small nanoparticle size here. Then if you go to a single crystal, which is a very large crystallite, in that case, you have a very sharp peak to deal with. Be aware of the difference between the full width half maximum and integral breadth. Some papers, they actually calculate the width of the peak in different ways. I'll distribute this slide later. You can see what it's about. Also, you need to actually, what kind of function you're going to use, or the collaborators is using for the distribution. There are many ones you can use. How you correct for the instrument. Basically, you can actually do correction using like subtracting the shape from the instrument using standard Gaussian, Lorentzian. One case that I like to show is this. Let's say a copper material where you have, for example, a peak at 40 degrees, 1, 2, 3, 4, 5, 6 samples, the same peak at different broadening. You have, take, for example, 3 researchers that will do the analysis for you, some of the best users we have. Basically, each one is going to do the orientation in one particular mode. Look at the correction. This is just a direct subtraction. This is a square root of the squares, Gaussian. And this guy here, Johnny, is more sophisticated. He's doing like a mix of that. And look at how much difference in terms of grain size they obtain. If you're dealing with like large, broad peaks, the difference is not large, but for sharp peaks makes a whole world of difference. So in a nutshell, what you actually want to look at when you compare what the technique has been using, what method they use for actually process the data, and so on. And don't forget to talk about the person who manages your X-ray instrument about what calibration was done for the grain size. Let me move quickly here. The other things like, okay, how about I'm having problem with my phase identification to find out what I have in my sample, and with my quantification, how much I have in the material. So basically, what can you do to help me here? Now, the peak areas from my phase, they do not match the compositions that I got from the software, is unexpected, and so on. First of all, you have to understand the first thing is that you have to use integrate intensity, the area of the peaks, not the top height of the peaks. It makes a whole difference. The peak area is much less sensitive to measurement changes, change in the sample. And also you have to watch out for like a change in the relative area of the peaks from one phase to the other, and that is due to the preferred orientation. Very scary slide. I just want to put this here to show that the basic equation of intensity XRD has a lot of factors to be taken into account, absorption, actually geometrical factors, and the structure factor. This is the same equation open up now with more details. Very important here is the linear mass absorption coefficient, and also the atomic structure factor, which carries information about the atomic structure. They all enter there to give you the intensity. Now, with all these equations that make you easy, it's very important to remember that part of the equation, it's a constant for the instrument or physical constants. And the other one are related to the material properties. So that's why people write this in a simplified way. And then that's why if you actually, you're gonna use an equation like that for a mixture, in terms of, it's difficult to calculate from basic principles for a mixture what the intensity should be, because you have the mass absorption coefficient of the mixture here, and that requires you knowing exactly what the mixture components are in terms of percentage. And that's what you are looking for. It's a kind of catch-22. But basically, in a mixture, if you start rationing, if you take like one phase ratio to the other one, you start eliminating factors here that becomes much more convenient. There are many methods around, and you can see here that they all use some ratio of intensity between phases. IRR is the common one we're going to talk, but there is always a correction that needs to be made when you use that. So one example here, you have a sample that you have done the analysis. The first thing you need to do, watch out about the amorphous background. So that's why if you use like if you make a background correction, or if you use a sample holder that actually is low background, so you can eliminate that portion. That's important if you want to find out the percentage of crystallinity or order in the material versus the disorder, amorphous. In that case, you want to make sure that you did remove the contribution in the background from the sample holder. Many people do forget that. So if you're going to do that type of work, it's very important that you contact your lab manager to make sure that you are using a holder that has low background, that you can subtract that. So what you want to do next, typically people want to find out the phases. They do like a peak shear, a peak fit to try to mark the peaks. They run against a materials database to identify what it is. It's sometimes automated process. You find like a number of phases. In this case was calcite. There are some peaks that you did not find in that search. So you do a second phase search and you find another phase similar, which is a dolomite. So they are similar forms, calcium carbonates, but this material has actually two particular phases embedded there. And of course, the natural question is how much of each phase. This is the mistake people do. People just look at the area of the peaks. Okay, so this peak here has an area of like, let's say call this 1, and this one here has a rate of 0.75. Okay, no, I know that this phase is actually 0.75 of that. That is absolutely not correct most of the time, because these phases, they have to be corrected. But remember, by some correction parameters that is coming from a standard where they actually have intrinsic properties, materials properties and scattering properties for the material that need to take place before you do that correction. So once you do that, you can actually come out like an estimate of one phases versus the other phase. In this case, that was using this IRR method. It's very simple method. Best method to do is Rietveld refinement, gold standard, because what you do here, you actually refine and you fit the whole bed that you actually start with the data, you actually have a preliminary structure, you create a model and you use a list, non-linear least square minimization, and you can have parameters that you can play with, and that can gives you actually the quantification, the percentage between the phases. This was done here. You can see here that you get a quantification. So there is a lot of pitfalls. You can get atomic structure, the 3D reconstruction of the material, the structure that you got. There's a lot of pitfalls when you do quantification. Most of them we see is that people are using the wrong type of calculation for the peak areas. They are not taking into consideration the correct corrections for the peak intensity. There are many methods over there, and including Rietveld, and they actually do not have the proper data for actually, the data is not with good enough data density for the structure refinements. Let's quickly move on. Okay, what else? Well, I can see that, you know, my peaks are different from the reference. Some of them are even missing. Let's see this guy run like a copper film, and basically he's just seeing 2 peaks. Where are the other ones? What is going on? Who stole my other peaks? What is going on here in this case? Well, why you are not seeing some of these peaks here that should be present? Well, what you might be having is something called a preferred orientation, where in that material, not all the grains are randomly present. You have just a strong direction that's preferential. Where are the other phases? Pole figure measurement is typically done there. It's a measurement where actually you are going to use other rotations like the tilt of the sample and the azimuthal spinning rotation, or only this rotating the angle of incidence to find where the other direct or the other crystallographic orientations went to. You go through like a projection here, and you get a pole plot for all the plugs, tilted plugs. And based on where they are in this pole plot, you can identify how they are located, symmetry, what shape they have. In this case of the previous work that I just showed here, when you actually do a pole figure project that looking at all the directions, you can see that the 111 pole, the 111 grains, they are located strongly oriented around the surface normal, but as you go out of the plane, they are randomly oriented. Look at the circular distribution. So if you put, for example, look for the 220 where it is, you can see that again, out of the plane, with the center is normal, and this is like a tilted plane, it's totally random oriented. So as you start dealing with samples that are more like highly oriented, you have to start exploring all different types of different rotations that your instrument will allow. This case is like a tilt. The type of texture that we see here is called fiber, because it actually looks like a fiber that's like oriented in the vertical direction, surface normal, it's totally random horizontal. If you do like tilt scans, you can get information about the amount of twinning that you have in the material and so on. And actually you can use that for like, you know, a whole pulpit study of your material. And basically, I think you got the image there, the message there, that if you start dealing with more oriented stuff, you have to start using pole figure. There are different methods listed here where the scans are more sophisticated, and you have to use an instrument with better capability. Now, additional scan modes is very common, like especially in the thin film community. People would come here and say, well, I did like a scan, two-theta scan in my material, and I just saw one peak corresponding to one orientation. I'm sure that this means that my material is perfect single crystal. There is no other orientation. But then he goes back, talk to his supervisor. He's not sure about that. And some reviewers or colleagues say, have you done rocking curve, for example, to analyze that, or a pole figure? So what I'm talking about is, for example, this thin film case here, where the researcher, they actually did our regular 2-theta omega scan. These are different deposition parameters. And what they see is this is the film, and they just see one set of peaks for the substrate. And this here is one set of peaks, only one orientation for the film. So it's a very good indication that in the growth direction, you are actually having a film that's very highly aligned to the substrate. That's very desirable in many applications. But then the question there, someone in the back of the seminar presentation tell, well, how about the other direction? Because your 2-theta omega scan just probes in one direction. And that's why when they actually look at planes that are tilted, they actually prove that actually the planes are actually correlated to each other. And in this case, they actually show and prove that like a cube on cube perfect epitaxy relationship. You can also use another thing that is the concept of omega rotation, and basically look at here that actually in this case, this is the plot, the video we saw before, your regular omega 2 theta scan. You are probing a direction along the scattering factor. But when you do the omega scan only, you are doing what they call rocking curve. In that case, the detector is locked at 2 theta, and only the sample is rotating or the angle of incidence. And in that case, you are probing a direction that is parallel to the planes, which is more sensitive to materials quality in this case. So it's a very valuable, actually, tool that you get. In this case, the researchers, they actually use that in their favor. They have a bunch of films. They want to identify the quality. They use the rocking curve. They just turn the sample with omega scan. If the sample is highly oriented, what they would see is that as they tilt this, the peak will be very sharp because the peak goes off the diffraction condition. But if they start tilting and the peak is very broad, that means you have orientation distribution that's large. It's a lower texture. By looking at the width of the peak for rocking curve, you can identify material qualities. Again, the second topic here, especially if you are working with thin film, don't fool yourself that only doing a 2 theta omega scan will do the job for you. You do need to do more sophisticated scans for that. So now, coming back to high resolution. High resolution is a wonderful technique. It lets you see things that are typically buried in the information there. This particular case, we have a researcher that was doing like a epitaxial material, he believes, very close match material that do deserve actually high resolution. And basically, this is the structure, the substrate. We have a relaxed film, and this silicon top fits that strain. This structure goes directly in your Pentium processor nowadays. In fact, this is similar work to what actually many of our students who graduate from our lab, they did, and they're now working in Intel. So in this case, they did actually a high resolution work, and they said, look, I saw this blob of peaks. I cannot identify too much what is going on here. Perhaps my sample is bad, you know, I don't have anything more to do and tell about this. So that's where a technique called reciprocal space mapping becomes valuable. So basically what you do in that case, you know that you are dealing with a single crystal. What you do is like you are kind of magnify, enlarge here, you are gonna actually have your probe size smaller. So you can actually see details of how that peak is shaped in the reciprocal space. How do you do that? Well, in order to actually have high resolution, you start by actually limiting very much the spread of the 2 theta angle by confining the acceptance in the detector. That means you limit the probe across the Ewald sphere. You also limited the spread of the beam coming from the source. So when you have these two effects combined, your box that walks around, your like probe that in reciprocal space is minimized so that you can start seeing fine features of those spots. This is done by actually adding some like layers of crystal diffraction in front of the beam or before the detector, or using very small apertures in the detector. We have all these varieties in our lab. This is typically used for cases of epitaxial growth. You have the substrate here in one case. You have like the sample is actually strained with a larger lattice parameter. The substrate is smaller or relaxed. The key here that as you look at these structures in the reciprocal space, they have a different position relative to the substrate dots here. They may even have a different angular position there. You use this in your advantage so that first the same measurement that you were gonna actually, that you did the scan, it becomes actually this one. This is actually the actual receipt. This is a two-dimensional distribution of this convoluted measurement you just did. Now, how can this make total sense? This is like a mass of intensities. Basically, it makes total sense because we are probing a tilted plan called 224 for this structure, so that we can look information about in-plan lattice constant. And you can see the expected peak positions is actually you have a substrate peak in the middle, which is given by this guy, a strain top layer actually around here, and you have the buffer layer silicon germanium down there. So it totally match what you were expecting. In addition, you got those peaks that are actually overlaid against there additional peaks that are coming up there that you are not expecting. They actually are the cause of this broadening. And now when you talk to the crystal grower, they say, yes, we wanted to increase the percentage of germanium in this layer so it's relaxed. We gradually increased the actually percentage until you get this number here that we found out. With these peak positions and the high level of accuracy we have in the reciprocal space, we were able to identify all the lattice parameters in the growth direction, in-plan direction. We could get the strain formation. We could calculate the amount, the percentage of germanium that is in this layer, and so on. And furthermore, we could look at the broadening of these peaks. Depends on how the peaks are broadened, which direction. We could calculate like vertical coherent length, 14 nanometers, which is pretty much match the thickness of this layer. We found even like the misfit dislocation in average without having to do even TM on this sample. So the shape of the reciprocal spot dot when you do a mapping tells you a lot about the features that you may actually find there. It's a very powerful technique you can use. It's most suitable as you start working with single crystal high quality materials. Now, I'll show you like a final example. It's like the state of the art of screw ups, because basically what you have here is a combination of a series of problems, and almost everything went wrong on that with that data. But we have to be patient because everybody's learning, people are learning, people know when they start using the technique. A researcher came to us and said, look, I have two materials, a sapphire substrate, and then the top is gold film. But in one case, I put like a buffer layer of 10 nanometers of titanium. And I expect this one here with a polycrystalline, and the other one is going to be epitaxial. So then the user showed me this data. I hope that the user is not in the audience now, but I'm not going to give any names. So when he did the epitaxial sample, he saw just 2 peaks, which was a good indication. But I was concerned a little bit about the quality of this data. When he showed me the data for the polycrystalline sample, we are kind of surprised. Where are the other peaks? Because if it's a polycrystalline, there should be plenty of gold peaks around. And the first thing that we start looking here is that, look at this data. It's very, very small step size, extremely noisy, to the point that we don't know if this is actually a peak or what is going on here. So the first thing you see is that he used extremely small step size. Now, to compound mistake, he used very fast scan size. So he used totally opposite of what actually needs to be used. Very small step size, extremely fast scan. The instrument went over this very quick, and everything close to the background is just noise. So what we recommend him is say, look, you probably are looking for peaks that are very close to the background. You don't need that small step size. You probably actually need like a slower scan speed. We did that. Look at how the data looks much more defined. We're going to show the final one here. We still have this difference between the intensities. This peak is from sapphire. We're puzzled about the other intensities. So then we start saying, well, if anytime that we have a thin film, that things start getting weird, we actually move to the position where this gold peak should be, and we start actually moving doing rocking curve, using the other kind of scans that are available in the instrument to see what's going on here. We explained that as we did the rocking curve there for both the epitaxial and the poly, we showed this, that the epitaxial film had like very nice rocking curve at the expected location. But the polycrystalline had a peak that was way off from the expected location. And we were puzzled that when the user did the first scan, he was missing intensity because he was working here. And why we have that particular tilt? So basically what you have is that is very common, is like a crystallographic tilt. between the film and the substrate, where actually the film, instead of growing like in the same orientation, it gets a tilt. In this case, was actually over like a fraction of a degree or a degree here. And then basically this is what we did, you know. For the epitaxial, we did that. We scanned this, they scanned down. You see, much less noisy than what was observed before. We have a happy ending here because you have the substrate, sorry, you have the substrate peaks, and you have gold 111 and 222, which is it's consistent to actually that strong orientation of that sample. For the polycrystalline, once we did actually the scan after the alignment, you can see here that actually the peaks that were missing originally, whereas the 222, 311, they actually start showing up. Very clear here, proving that the sample is actually polycrystalline. And in this case, here you can see we did a reciprocal space map of the epitaxial one. So when the user initially just put the sample and did this scan, this is actually the one for the polycrystalline. So when the user put the epitaxial sample and did the scan, this is what actually he got there. And because it was easier for him to get the data because it was across the actual main peaks. But when he put the sample that's polycrystalline, he was scanning off the film peak by a certain fraction of a degree. He was not. And then as we actually align and maximize here and do the scan, he was actually in the right location. Okay, I want to end here, but I'll go through. There are a few other common problems we see in other tech. I'm just going to mention here, for example, Sachs and Juan Lopez did a very good webinar a few weeks ago. We see problems where people, like when they subtract the effect of the buffer or of the capillary, they end up subtracting too much or subtracting too little on the data. Also, they put too much material and there is a huge aggregation that affects the beam size. Technique that's called XRR. One problem we have is that sometimes people use very small samples compared to the beam size. In this case, you start seeing very weird shapes when you align your material. What end up happening is this case is like the same sample we did analysis. This is like a large sample where it's larger than the beam for the measurement. This is a small sample, much smaller than the beam. And you see, in addition to like alignment problems, you actually lose a huge dynamic range that's involved there. So summary, what you take home from this? Well, I think the main message here is that when you start comparing what you got with other people got, or someone brings you, ask questions. What was the exact measurement conditions that was used? Number two, when you do measurement, choose your measurement conditions. This thing of going blindly like a zombie to the X-ray lab and putting your sample there and running, starting the measurement, and then going home with the data and trying to understand everything there, that doesn't cut nowadays. Try to see if are you really using the proper configurations. Understand the options that the instrument has. We have wonderful tools with lots of different options. Explore those. If you are preparing powder samples, make sure you do a proper sample preparation. Preparing the sample properly will save you a lot of headaches, a lot of complications in the data analysis. In particular, if you're doing thin films, it's not a question of just sticking the sample in the instrument and going and running away. You probably need to do some maximization of the intensity. You're gonna have to use multiple scans that are available on the instrument. Nowadays, most of the instruments have multiple scan options. Think about reciprocal lattice points, where you are you choosing the proper choice? Are you making the proper choice at your advantage for the analysis you need? And very important, make a proper balance between the measurement time. Again, scanning too quick might cut for you in some cases. Scanning too long might give you even wrong data. You have to understand what your material is. You have to be smart on that. Do not try to extract like parameters from quantification or Rietveld refinement if your data is lousy or is too noisy, right? That's basic. But in a nutshell, there are things that you can control. There are things that's up to the instrument. And then the name of the game here is that if you see something that looks strange in the measurement or during the data collect, ask question. It's very common that we see people coming to us after they have collected 10, 15 measurement with actually wrong settings that are different from when you actually gave them the training. So thank you very much for attending this. Thanks for all the audience throughout these webinars, all the presenters in the previous talks, Julie for actually taking the leadership and being like the main person behind this, the logistics of this, staff for the communications. This is the contact information in the X-ray lab. If you have any questions, please let me know. Otherwise, send me an email. Video is going to be posted soon. With that, thank you very much. I'll go back to Rick.
Well, thanks, Mauro, for that very interesting and excellent talk, very dense. I'll let you catch your breath a little bit. We have a few questions that I can begin with. So is it correct to use the Shearer equation to calculate the grain size and grazing incidence 2 theta measurements for a particular peak?
I have said that you have to be, yeah, good question. I have seen people, you have to be careful when you do that because you have to bear in mind that you are probing a different direction. I did not have the time to cover glancing incident XRD. You have to make sure that the sizes that you are getting are actually, and you report them for those particular directions. Having said that, it may be a very good idea because if you use a glancing incident and you have angles that are very small, you may be actually using XRD to probe grain size that are almost like in the direction along the surface, which is different from what traditional people probe. We'll be happy to discuss detail with the person. Send me questions on that. That's a very good question.
Okay, thanks. If we're working with a polycrystalline ceramic powder, then what will decide the quantitative phase portion? The intensity corresponding to that phase or the number of peaks present in the XRD pattern?
Well, basically you get like when you get a number of peaks, the phases that are present, they are not necessarily the number of peaks. I think if I understand the question correctly, what you do, as I showed there, I show an example of the calcium carbonates. We have a number of peaks, but only 2 phases present. And I think you use like a database or a reference guide to try to identify the phases first. If there are peaks that are not easy to identify, then you have to talk to us. And then we have to start thinking about doing automated search match, and you'll be surprised. There was a case once that we did a material and there was 2 phases present, but then there was like a 3rd phase that we could not identify. And when we did automated search with the computer, it was suggesting actually aluminum. And then as the researcher went back to his lab, he found out that someone has annealed aluminum in the furnace that he used just before he prepared his sample. So again, there are surprises that you can get there. So I'm not sure I understood the question, but again, feel free to email me the question and I can be more precise. Thanks.
Okay, we have another question. Is it true that the higher intensity peak will be a major component of that powder, or is it depend on other factors too?
Good question. I think it's, well, when you see like a strong peak there, you always have most of the time to say, okay, that is probably going to be one of the phases present. But it depends. You might be, for example, say you run a thin film, you see the strongest peak is silicon. That's not the phase, that's just the substrate. And you may have like a situation where you have very strong preferred orientation. So I think looking at typically we all do that. We all start looking at the actually strongest peaks, but we have to be alert for like preferred orientation where that peak is maybe strong artificially because of sample preparation, or it could be like a real effect there. One of the criteria that people use when they do phase identification is to try to match the 3 strongest peaks against a certain phase. There you go. You see the strongest peak is always a good parameter for you to use, but you have to use with caution there.
Okay, the next question is actually quite good. So many people report the XRD pattern of single layer 2D materials. Is it possible to get the XRD from such a material?
Single layer 2D materials?
Yeah, like graphene or something, or
Correct. Yeah, I think that depends on the material. People have reported that. I think you have to be very careful in terms of the amount of intensity that your scattering intensity is not very high, especially like the disulfide. I have seen reports. I have seen people trying to attempt to do that with graphene as well. It does work better if you are like in a synchrotron beam, where you have like the beam coherence and the intensities are much higher than the lab source. So it's possible to do in some case. but you do need to play a little bit with the settings of the instrument to try to get that.
Okay, thank you. So we still have about looks like about a half a dozen more questions to go. Are you still up for
I'm
answering
game.
questions?
I'm game. It's up to you if you want. We can go through, and I see people can walk out the if they have other things there.
Okay.
So go ahead.
So what software do you recommend for Rietveld analysis?
Oh, that's a very good question. We have many. I think we in-house here, we use the MDI Jade software mirrors. I think Topaz from Bruker comes with our instrument. We have that as well. We also have High Score Plus. I believe the manager of the X-ray lab now, Juan Lopez, is very familiarized with one that is keep my mind now, but maybe Juan can actually add that name later. That's a free distributable software. Is it? I know that GSAS was a famous one, of course, people favorite. It has a little bit of a steep learning curve. There is one in our lab there. Juan, feel free to remind me what software you like there.
FullProf?
What? FullProf, yeah. FullProf has the advantage of a very clean, nice interface and free to download. So that was the question.
Can you explain basal reflections?
Basal reflections? I'm not sure what he's talking about, the basal reflections. I think for the hexagonal structure, you have like basal planes that you can see there. Depends on the orientation of the crystal. So if you can send me specific about that question, or you can send me that question again, we can call each other to understand what's the context there.
Okay.
But we see like sapphire hexagonal system. We see like basal planes. Yeah.
Okay. What is the procedure to probe a tilted asymmetric plane in RSM?
Yes, very good. This is mostly done, it's more fun to do in front of the instrument. What you do basically, you start with your sample, normal alignment. You look at the planes that are parallel to the surface, the symmetric ones. You get your alignment start there. Then what you do is that you need to kind of know the structure you have. It depends if you're doing silicon, if you're doing sapphire, or there are some candidates that we recommend you to do. And then let's say in silicon, like I do the example, I use the 224 because I know that's a plan that is like, it's low angle of incidence, but not too low. And it gives me very good intensity. There are some other candidates, but they are either very close to the surface or they are like a 2 theta extremely high. So that means my intensity starts going down there. Then I go there, move there, and then what you need to do is the azimuth of the phi rotation needs to be optimized very, very carefully. It's a back and forth process, but once you are done, basically you program the instrument to do that. If you are in campus, please feel free to stop by. If you're out of campus, I'll be happy to call you, or you call me so we can walk you through the details there. Thanks.
How do you subtract the holder background from scans in Jade or High Score?
Oh yeah, that's a very good, that's a complicated thing. So first of all, you have to make the odds in your favor. First, you actually do a measurement. You measure a background holder signal with the exact same conditions of your sample. And then you can actually do that, and there is an automated way to do the background subtraction in Jade or any software, but you have to be careful that you are not over subtracting, because when you have your sample, you have some absorption that suppress the beam. When you don't have, so this signal of basically you are actually seeing more of the holder than you do. So basically that is something that you have to be extremely careful that when you start seeing over subtraction. In SACs, this is done beautifully because you do transmission. You can actually correct for the transmissivity of each of them. I think the best way is not to, if you have some Rietveld to do, not bother too much. Try to use, there are some commercial holders with extremely low background. They will not interfere too much. That's the best way to do. In terms of the hands-on, the software specifically, we can show you, if you're using Jade, how to do that.
Okay.
In the lab. So,
what is a good sample rotation speed for the sample holder? One of our background silicon sample holders has started showing peaks from the holder itself. Why is this, and what can be done to prevent this?
Yeah, I think you might have well, the rotations that, I have seen people spinning the sample too high and moving powders around. You have to consult with your instrument. I think here we have some guideline. I think we use 1 RPM in our Bruker machine. Now, if you say that you start rotating and seeing peaks from the substrate, it means that basically the sample is actually does not have like a square shape. It depends how you rotate, you expose. Oh, you talk about the substrate or the sample holder? Because if you're seeing more of the sample hole, that means your sample has a regular shape and depends on the angle you expose most the sample holder. If you actually expose more of the substrate, that means that you have an alignment issue there, that as you start spinning, basically in one direction, the substrate is better aligned or not. So again, if you are in campus and working in our lab, I'd be happy to look at that. That will be a fun thing to check. If you are from outside campus, give a call. We can try to help you there. Okay. You guys are having very good questions, by the way.
Looks like 4 more. You still up for it?
I'm all for it, yeah.
Okay. When performing Rietveld refinement, how do you account for preferred orientation? I'm always worried about overfitting the data.
Yes, that's a question that maybe we can discuss together. Juan is the master of Rietveld as well. It's basically, there are features that automatically you put in the software. And basically you have to, in the Jade software, there is a box that you actually click and you actually refine the data and see if it makes sense. If not, you have to go back. I mean, without seeing a specific data, it's difficult to do general recipe. But why don't you again look for me, look for Juan? We can talk to you about that.
Okay, here's a follow-up question for the person with the ask about basal reflections. So I work with minerals and I have seen quite a few reports which talk about basal reflections. However, I haven't been able to see those particular peaks in the samples. Samples he has. Does it work by enhancing the preferred orientation in the minerals? Can you suggest some methods?
Yeah. Oh, minerals. Minerals actually there are especially I don't know if you're talking about clay materials or what it is, or just pure minerals. There are tricks that actually people do in sample preparation that can actually emphasize and to look for some particular phases. We have done a considerable amount, especially for like geological survey in the past. And again, if you have actually the reference to send us to look at the problem we're looking at, and I think we have had situations where most of the time we did not even need to do any sample preparation change for that. But it's case specific. Again, very good question. Why don't you shoot me an email? My email is here in the third one here with that reference. We'll go over that. Yeah, there are actually books about that. We even have a book here in my shelf about that. So.
Yeah, and they responded, they are clays.
Yes. Oh, yeah. Clay material is actually, we have a lot of horror stories with clay. Mm-hmm. There is one guy who used to clean his sample holder with alcohol, with a liquid, and did not dry properly. He put a clay soaked the thing, and his peaks are all over. We found out it was that thing. Some people would put some actually, do some preparation. There is a fantastic book, X-ray book, that's one guy in campus that used to have. He retired now with all these recipes. I'll find the name and give that to you, or you can do something in the lab here.
What do you believe is the best technique to prepare an XRD sample? How do you balance between making the sample flat without inducing preferred orientation effects?
Oh, yeah, so while preparing like, grinding the sample by hand, a pestle and mortar is good enough. I think you can use like more tools for like grinding, ball mill and so on. But the key thing is actually, when you actually handle your sample, if you can touch, I know samples you can't touch, but if you actually touch it and see like it's more like a sugar grain type of thing, it's too coarse. Now, one thing that I see a lot that's a problem, when people put the powders in the holder, they tend to push them down from the top. That can be a disaster for some materials because they can easily create a preferred orientation. What we do in the lab, Mohammed and Juan, they teach that. They even have a video on that as well that's coming up where actually you just like sweep from the top. We also came with the new X-ray machine. We make a tool that you can actually load from the back. So you load the powder from the back so that you minimize preferred orientation. Talk to us, we'll show you.
What do you recommend for collecting rocking curve on a film? Oh, move.
On a film what?
What do you recommend for collecting rocking curves on a film peak when it is overlapping with another peak?
Yes, if it's, well, there are tricks here. One thing is that when you see the overlap, you're seeing the overlap into theta omega scan. Is that the question? Because if you see the overlap into theta omega scan, and then you do an omega scan there, your chance that you might be able to see them apart in the reciprocal space. Now, if you don't see, then you have to go back to your configuration. Can we use like a smaller slit or a smaller acceptance detect? Because then you can start having better chance to separate them. And a reciprocal space map could be one situation where actually two peaks too close, you can separate them. Those are things. There are tricks into, I think, basically look for the lattice scan you were talking about. Second, see if you can actually use smaller slits. So to separate these peaks, consider reciprocal space map. Nowadays, it's very fast with the new detectors. Or talk to us for specifics.
Okay. And Brandon House is hi. Hi, Brandon.
Hey, Brandon, how are you?
So it looks like that's it for the questions. So if anybody wants anything else, it's going once, going twice.
All right.
I think we're done. So
okay. Thanks, everyone. Thank you, Rick, for doing this. Again, thanks for everybody. Fantastic series. You're close to 2,000 participants there. Appreciate everybody. Thank you. Back to you, Rick.
Yes, and thank you for that very excellent and very informational talk. So with that, I'll probably close out the meeting.